Hello, good morning. This is re-recording of Lecture 4, Conceptual and Logical Design. First one, we'll want to just distinguish the difference between data modelling and systems design. They overlap to a certain degree, but I think it's useful to consider the differences between them. So, data modelling is the process of organising data, the data elements, the elements in the data, and standardising how what those elements are and how they relate to one another. It's the process of identifying, defining data elements and their relationships. Systems design is a more encompassing activity, which is the process of defining the architecture, components, modules, interfaces and data for a system that satisfy specified requirements. So data modelling is a subset or is part of overall systems design. Systems design, there are many design, what are called design methodologies, approaches to designing systems, computer systems. And one of the earliest was the waterfall development model, which is a linear model that originated in Bennington in 1956. At this time, when this was the beginning of the development of large computer systems or reasonably sized computer systems, and there was no established methodology for building such systems. So what Bennington did was look at analogous situations, and he looked at the manufacturing workflow models, which are relatively linear processes operating within factories, and he took that as the model from which to develop the waterflow software development model. And we'll be revisiting system development models in a later lecture. Basically, it's a linear process. You define the requirements for the system, you decide whether it's feasible, you design the system, you construct it, you build it, you implement it, you test it to see whether it in fact does what you want it to do, you roll it out across your organisation, and then you review the process. Has your system delivered what you want to do? And the data modelling component of the design process mostly occurs within the design stage of the waterfall development model. So why do we care about data modelling? Why do we bother? Well, a report by the Organisational Aspects of Information Technology Special Interest Group in 1996. It's a bit old now, but it's still a reliable source of information. Identified that 80 to 9% of software solutions do not meet performance goals. Many are delivered over budget. A similar number are delivered later over budget. 40% fail or abandoned, and less than 25% fully integrate business and technology objectives. If you think back to the news, this is a particular problem for sort of particularly large systems. Think of the NHS, the National Health System databases, and the delays that have occurred over some of these large governmental systems. The report not only looked at how successful software development was, but also why things failed. What were the underlying causes for the lack of success of software systems? 3 were identified: insufficient requirement specification. If you don't know, if it's not exactly clear what needs to be built and why it needs to be built, it's unsurprisingly that not the right thing gets constructed. The second problem was a lack of appropriate design methodology. Without an appropriate design methodology, the efficiency of development can be greatly reduced. The third problem was poor decomposition of design into manageable components. So you may have a design that you want to implement, but if you don't identify the correct components that you need, that are required to implement that design, that can cause a lot of problems with the design itself, with the implementation itself. So what has formal design process ever done with us? This is kind of an inverse to the previous slide, but with a few additional things. Following a formal design process helps to identify and prioritize user needs. If we don't know what the users need to be able to do, we can't build the appropriate system. It helps the team to understand the data and manage its complexity, in particular, avoiding redundancy, duplication in the data. If you've worked with, I'm sure many of you have worked with commercial, corporate organizational data sets, you will often find that the data is to a certain extent inconsistent. There may be data for certain areas, but not in other areas, missing data, and it is only through the data modeling process gives you an opportunity to explore the data and its complexity. Helps find gaps, errors in information and data before development takes place. Quite often high-level managers know that a data set exists, but perhaps are not aware of the problems that exist in it. Its consistency, whether it's got missing values or whether there are erroneous values entered into it. It's a means of documenting the system. System documentation is very important, not only because we as individuals forget through time what we have done and why we have done it, but also increasingly in the modern age of rapid staff turnover, you may have to be passing on your work to other people who need documentation to understand how the system operates. It helps communicate the system and the data relationships in an accessible graphic form. This can be really important when you're presenting the system to the people who are deciding whether to implement the system, who have their fingers on the purse strings of the money that's required to develop the system. It helps estimate the time and cost of development. Many IT systems overrun in cost and time. For example, my rule of thumb is that I estimate how long it's going to take me to undertake some kind of development, and then I multiply that time by 5 to get a more realistic value for that development time. And the last one is that the formal design process gives you an opportunity, gives an organisation an opportunity to review how the business actually operates. The identifying of the relationships between data items, what they are, and their relationships may identify aspects of business processes that could be improved ways of data capture, for example, or that data is captured at some other point in the business process. Well, when it comes to design, or is data modeling design, 3 levels of design are identified. We can identify 3 levels of design. We have conceptual design, which is effectively an executive summary of an entire enterprise. Its role is in communicating what a system is intended to do and who those users are, but not the details of how that is to be implemented. The logical design is the second design stage, in which a fully specified model is defined for the system that is independent of any particular technology. So this is a design that could be implemented in a number of different database management systems, depending on the idiosyncrasies of those individual DBMS. The final stage from the logical design is the physical design, where the logical design is implemented within a specific software solution, be it Postgres, MySQL, Access, or any database system. So the progress from conceptual through logical and physical includes an increase in detail and specificity. The next slide, I won't go into it in any great detail, summarizes the difference between conceptual, logical, and physical models. As we can see, the scope is different. So conceptual models, the audience is for a general audience and to communicate and agree about system scope and content. The objects should be high-level data structures, and business areas should have a relatively few number of objects depicted on the page, relatively informal. And as we can see, we move through the logical to the physical model. The detail in the model increases. So for example, by the time we're on a physical model, we may have hundreds of data objects described over multiple pages. We move from an informal to a formal notation, etc. You can look at that in some detail or digest that in your own time. This slide also shows, illustrates this the progressive nature of the data modeling process. So at the conceptual level, we're interested in entity names and relationships. By the time we move into the logical phase, we're not only interested in the entity names and their relationships, but also their attributes and the key relationships that connect these entities together. And by the time we move to the physical model, we're converting entities into physical tables with particular names on columns and the particular data types assigned to columns. So it's a process of increasing the specificity of the model. And if we overlay the conceptual, logical, and physical design processes onto the waterfall development model, we can see that most of the conceptual component, the conceptual modeling occurs in the requirements, the feasibility, and the early parts of the design stage. The logical modeling is primarily part of the design phase, and the physical modeling straddles both the design phase and the construction phase. I should make a point here that while the waterfall model is linear, there is a lot of feedback that goes on between these various levels. So for example, during the construction, during the physical implementation of a logical design, that may throw up new information that may feed back and result in a redefinition of the logical model. So the next lecture will be about physical design, converting the logical design into a physical design. This lecture is concerned with the conceptual models and the logical modeling. So conceptual models. Well, a conceptual model is an abstraction of the world designed to facilitate understanding of the concepts, entities, and relationships within a system. It's there to simulate discussion, explain relationships, but also to provide a documentation of the system at a high level, effectively an executive summary that is relatively easily understandable by all people involved in a project, both managers and computer tech programmers, for example. So here's I'm going to show you just a few examples of conceptual models. It's actually quite hard to find conceptual model diagrams of GIS systems online. So I've included a couple. that aren't. For example, this one, which is a conceptual model of the water cycle. And if we compare it to the table on the previous slide, we can say, yes, there's about 20, there's less than 20 entities. The arrows, which are identified with both with graphically and with descriptive words, and we've got the arrows showing the flows and the connectivity between the various entities involved in the water cycle. Here's a very different type of conceptual model. This is for the Gulf of Mexico Estuaries Integrated Science. In this case, it's showing four different areas where information is required and needs to be brought together to help develop predictive models of estuary water quality, for example. Here's a third example, which is a conceptual model known as the place diagram, which shows the relationship between various measures of place, how people experience a location, and provides a conceptual model for the relationships between these various components. And it provides a hierarchical relationship, as we can see. So a place is divided into 4 different major units, which have further subdivided into other aspects of place. Here's an example of a logical diagram for the Flickr photo service. So this is far more closely aligned to database system modeling. And while this is not actually a logical model that was drawn up that was then used to build the Flickr photo sharing service, this is actually an example of retro-engineering where the Flickr service has been decomposed by Bryce Glass in this case, who has gone through the Flickr API and how the objects of the Flickr service relate to each other, and drawn this diagram to depict those relationships between these objects after these objects have been implemented and released by Flickr. So this is an example of retro-engineering, but is the kind of diagram that you might want to, probably quite a good example of a system conceptual diagram for a computer database-based system. Finally, this is a true GIS example, Astrium Navigation Systems and Applications Concept and System Diagram for location-based service, which was used during the World Cup in Germany in 2006. It shows the relationships between GPS, satellites, mobile communications, Bluetooth radio systems, WLAN networks, etc., etc. But it provides, the important point, it shows the various components of the system and how they relate to one another. Finally, here's an example from Esri, the Rhode Island DOT Enterprise GIS Architecture Conceptual Model. This is a system implemented with the Rhode Island Department of Transport. We can see the main entities are contractors, various workflows within the system, the government buildings, the health infrastructure, and we can see the connections that exist between these various database systems. I think the important thing to take away from the conceptual model is that they're very varied. You draw them to communicate what you want to communicate to the people you want to communicate to. There is no particular way of drawing conceptual models. You draw one that provides the information in the most appropriate way to the people, to the various users and managers of the system, decision makers. That's all I've got to say on conceptual modelling, really. So logical model. So this logical modelling, so once you've decided on what your system is going to do, and you've decided, you've gone through a feasibility study to decide that it's actually worth doing, you move on to the logical modelling stage. Now, there are two pathways that you can take for logical modelling, two basic pathways. If you're developing a relational database system, then you undertake your logical modelling is generally through entity relationship modelling, and then the definition of tables that you physically implement within your relational database model. If you're developing an object-based system, and we will have a lecture on objects and object-based systems later this year, then you would follow an alternative logical modelling process, probably through using Unified Modelling Language, UML. And I'll talk briefly about that at the end of this lecture. So depending on what type of physical system you're implementing, a relational system or an object-based system, you'll follow a different logical modelling process. Most of this lecture is concerned with entity relationship modelling. So, what is entity relationship modelling? Well, it's a logical modelling approach to help in relational design. It originates in Chen in 1976, and the original Chen paper is on the reading list. The purpose is to identify the components that make up your system, the entities of your system, the attributes, their attributes, and the relationships between entities. Before moving into how we do this and how this was presented, it's worth noting that the whole variety of notations have been used in entity relationship modelling. Which one of these notations you use is a personal choice. However, always consider that choice in the context in which you're working. So, for example, if your organisation has a particular style, then you should use the style, the in-house style of your organisation. And you should also probably aim to use one of the more popular, more widely used styles, as they tend to be more understandable by the layman. Also note that there are different ways of representing the same physical model as an entity relationship diagram. You can draw an entity relationship diagram that shows more detail or less detail, but effectively that shows in fact the same relationship. So there are different ways of representing the same model in an entity relationship diagram. Indeed, here's an example. This is where we're going. This is an example of an entity relationship diagram. And now we're going to work through the various components that make up this diagram, the symbology. First of all, entities. Well, what is an entity? An entity is a specific real-world object, concept, or event. So, for example, my dog Rover. And so an entity is a thing in the real world, and this in object terms is often called an instance. There's a bit of confusion over terminology. So instance in object terms, entity in relational terms is a specific real thing in the world. In object modeling terms, an entity is a collection of instances of an entity that share a common set of attributes. So, for example, pets. In relational terms, this is sometimes called an entity set. So this is confusing. So the word entity is used sometimes to return to a specific example of an entity, a specific instance of an entity, but it is also used to describe a class of entities, and those class of entities may also be called an entity set. So the entity set is a generalized or a template into which you record specific instances of those entities. So here's a few examples. And those entities also have attributes. So here's some examples. So the entities in a university database might be the students, the faculty members, the courses, and many other types of objects. Airlines may have aircraft, routes, crew, suppliers, etc. And a neighbourhood model might have roads, properties, retail areas, etc. It's important to note that entities, wherever possible, should be, real-world entities should map one-to-one onto the entities within the computer at a reasonably low level. So, for example, faculty members are entities in a university model. But you might think, well, admin staff do different things to teaching staff, to catering staff, for example. And that's very true, but they are still all staff members or members of staff, and there should be a common entity, staff, of which these are all members. And it is what they do, or the relationships to other entities, that define particularly whether they are a faculty member, or whether they work in the kitchens, or whether they maintain the property. It is a relationship between the staff member and the other entities that actually define what they actually do. These various entities have attributes, can have attributes associated with them. So within the university system, the student entity may have attributes that define the student number, their name, date of enrolment, etc. The aircraft entity in the airlines model might have an aircraft number, the total hours flown by the aircraft, various other attributes. A property